famously made even Albert Einstein a bit uneasy. Quantum entanglement.
The spooky action at a distance.
Exactly. But what if this spooky connection isn't just weird science, but actually the key to whole new technologies?
That's the big question, isn't it?
We're going to try and unravel how this fundamental phenomenon plays out in two really different particles, the electron and the photon.
Right. And see why their unique quirks, their differences, actually make them perfect partners for the quantum future.
So our mission today, yours and mine, is a deep dive into those core similarities, yes, but also the really radical differences between electron and photon entanglement.
And understanding these distinctions, it's crucial because they're directly shaping the future of, well, everything from quantum computers to maybe even a quantum internet.
We want you to walk away with a really well-informed perspective on this cutting-edge science.
A shortcut to sounding like you know what you're talking about at parties.
Maybe. So let's start with the basics, the universal weirdness. What is entanglement, really? It's definitely more than just, say, knowing one glove in a box means the other box has its partner.
Right, that's the classic analogy. But in that case, the information which was always there. It was just hidden until you looked.
Okay, so how is quantum entanglement different?
It's fundamentally non-classical. When particles get entangled, they essentially stop having independent, well-defined quantum states.
No independent states.
Exactly. Instead, they share a single, unified quantum state, a kind of shared wave function that describes the whole system no matter how far apart the particles are.
So mathematically, you literally cannot describe particle A without describing particle B at the same time. They're linked.
Precisely. Think of a specific example like a Bell state. In that state, particle A isn't definitely up or down on its own, and neither is particle B.
Okay.
What is definite is the correlation. If you measure A and find it up, you instantly know B must be down, or vice versa.
But those properties weren't decided beforehand.
No, that's the key. They aren't pre-existing hidden variables. They exist in this kind of probabilistic haze, only realized at the moment of measurement.
And we know this for sure. It's not just theory.
Oh, yeah, absolutely confirmed. It's been shown again and again by experiments violating Bell's inequalities. That's the mathematical proof that no classical theory, nothing based on local realism, the idea that things have definite properties and are only influenced locally can explain it.
Wow. Okay, that's a pretty big conceptual leap from, well, everything we see around us normally.
It is.
And this shared state relies on two key quantum ideas, right? Superposition and non-locality.
Exactly. Superpositions is that weird quantum thing where a system can be in multiple states at once, like an electron being both spin up and spin down simultaneously.
Right.
Entanglement is basically a more complex shared superposition, but involving systems that are separated in space.
And non-locality, that's the spooky action part.
That's the really mind-bending part. You measure one entangled particle, its state collapses, picks a definite value, and its partner instantaneously collapses to the corresponding correlated state.
Instantly, no matter the distance, even light years.
Even light years. If you have two entangled electrons, total spin 0, measure 1 is spin up.
The other one has to be spin down, instantly.
Correct.
But, and this is crucial, right? You cannot use this for faster-than-light communication.
Absolutely critical point. Yes, the collapse is instantaneous, but the outcome of any single measurement is fundamentally random, pure chance.
So you can't force particle A to be up to send a 1 bit.
Exactly. You can't control the outcome to send a message. You only see the correlation after you compare the random results from both ends using, phone call or email, regular classical communication.
Okay, good clarification. So where do these entangled states even come from in the first place? How are they born?
Often, they arise naturally from fundamental conservation laws, things like conservation of energy, momentum, or angular momentum, especially during particle creation or decay processes.
Like what?
Well, imagine a particle with 0 spin decaying into 2 spin 12 particles, like electrons. Conservation of angular momentum demands their total spin still be 0.
So their spins have to be opposite. Anti-correlated.
Precisely. If one is spin up, the other must be spin down. It's built in. We see this in processes like electron-positron annihilation, which can produce entangled photons. Or even in materials like Cooper pairs and superconductors. Those are naturally entangled pairs of electrons.
So the universe's own accounting rules, its conservation laws, are the source of this weird interconnectedness.
In many cases, yes.
All right, let's get specific then. Let's talk about our two main characters today, the electron and the photon. A real tale of two quanta. First, the electron. What are its key features for entanglement?
Okay, the electron. It's got mass, a negative charge, and crucially, this property called spin-12.
Spin 12. That number sounds important.
It is. That half-integer spin classifies it as a fermion, and fermions obey a very strict rule, the Pauli exclusion principle.
Ah, Pauli exclusion. I remember that from chemistry. No two identical fermions in the same quantum state at the same time.
Exactly. Or, more formally, their combined wave function has to be antisymmetric if you swap them. But how does this become a resource?
Right. How?
Well, first, those two spin states, up and down, make the electron a natural quantum bit, a quip,
Okay, the fundamental unit of quantum info.
and its charge, while making it susceptible to noise, also lets us trap it. We can hold on to it in things called quantum dots, manipulate it precisely. That's vital for building quantum processors.
But it's heavy, relatively speaking, and charged. So it's not going anywhere fast, and it feels the environment.
Right. It's a stationary or material qubit. Great for processing locally, not so great for sending quantum information over long distances. It decoheres too easily because of that charge and interaction.
And this Pauli principle, you said it's a resource for entanglement. How does a restriction help?
This is really cool. If you force two electrons into the exact same spatial state, same location, same energy level, and a quantum dot, for instance, the Pauli principle kicks in.
It says they can't be identical.
Right. So if their spatial state is identical, their spin state must be antisymmetric to satisfy the overall rule. This forces them into a specific, maximally entangled state called the Spin-Singlet state.
So you can use the exclusion principle to guarantee entanglement between electrons just by putting them in the same place?
Essentially, yes. It's a powerful, deterministic way to create electron entanglement, unique to fermions like electrons.
That is clever. Okay, let's pivot. The photon. Massless, neutral, a boson. Totally different beast.
Completely different. Zero rest mass, zero charge, and spin 1. That integer spin makes it a boson.
And bosons are the opposite of fermions. They don't obey Pauli exclusion.
Correct. Any number of identical bosons can pile into the same quantum state. That's the principle behind lasers, loads of photons in the same state, creating coherent light.
And being massless and neutral, that sounds ideal for travel.
It's the ultimate flying qubit. Always travels at the speed of light, CPU, and being neutral means it hardly interacts with electromagnetic fields in its path.
So it's robust for sending information over distance, less prone to noise.
Much less prone to environmental noise during flight, yes. But that same weak interaction makes it tricky. It's hard to catch photons reliably and hard to make them interact strongly with each other, which you need for building quantum logic gates.
Right, pros and cons. And what about its spin? You said spin 1. How does that relate to entanglement?
For a massless particle like the photon, its spin projection along its direction of travel, called helicity, is restricted. It effectively has two possible values.
Only 2.
Yes, and these correspond directly to its circular polarization, right circularly polarized or left circularly polarized light. So when we talk about spin entanglement for photons, we often really mean polarization entanglement. They're essentially the same thing in this context.
Okay, so summarizing. Electron massive, charged fermion, obeys Pauli, good for stationary processing, noisy. Photon massless, neutral boson, ignores Pauli, great flying qubit for communication, but hard to make interact.
That's a good nutshell view. Their fundamental properties really dictate these very different but complementary roles.
So now we know what they are. How do we actually make entangled pairs of these things? The experiments must be quite different. Let's start with photons. Optical methods.
Yeah, the absolute workhorse for photon entanglement is a process called spontaneous parametric down conversion, SPDC for short.
SPDC, what happens there?
You take a high-energy laser beam, the pump, and shine it into a specific type of nonlinear crystal. Occasionally, spontaneously, a pump photon splits inside the crystal into two lower-energy photons.
The signal and idler photons.
That's right. And because of conservation laws, energy and momentum must be conserved in the splitting. These two photons are inherently correlated. Their properties are linked.
And you can arrange it to link their polarization, too.
Yes. Using specific crystal types and alignments like type 2 SPDC, you can generate polarization in entangled states. For instance, a state where if the signal photon is horizontally polarized, the idler is vertically polarized, and vice versa in superposition.
But you said spontaneously and occasionally, so it's not guaranteed every time.
Definitely not. It's probabilistic. Most pump photons just fly straight through the crystal. But people have gotten much better at it, using things like periodically pulled crystals to boost the efficiency quite a lot.
Are there other ways to get entangled photons?
There are. Older methods used atomic cascades, but collecting the photons efficiently was hard. Quantum dots are also really promising. They could potentially give us on-demand entangled photon pairs right on a chip.
Okay, so SPDC is the main way, but it's probabilistic. Now, electrons. Entangling them sounds harder since they're stuck in materials.
It is a different challenge, yes. We generally rely on the strong interactions electrons have within solid-state materials, like the Cooper pairs you mentioned. Exactly. Cooper pair splitting is one cool technique. You start with a superconductor where electrons are already naturally paired up in spin-entangled states. Then you use a clever device, like carefully controlled quantum dots, to split these pairs apart, sending one electron to one location and the other electron somewhere else.
So you're extracting nature's entanglement and making it usable.
Pretty much.
Yeah.
You transform this natural, local entanglement into spatially separated, controllable, entangled electrons.
What about making entanglement from scratch with electrons? You mentioned quantum dots earlier.
Right. Gate-defined quantum dots offer a very deterministic approach. This is less about finding existing entanglement and more about engineering it.
How does that work?
You trap two individual electrons in adjacent quantum dots, using tiny electrodes gates to create potential wells. The electrons, being close, interact via something called the exchange interaction, which naturally couples their spins. Then, by applying precise voltage pulses to those gates, you can rapidly turn this interaction on and off, controlling it very accurately. This allows you to perform quantum logic operations, like a CNOT gate, which can deterministically create maximally entangled Bell states between the two electron spins.
Deterministic. That sounds much more like building a computer. You command it to entangle.
That's the goal, yes. Very high control. There are even more exotic ways, like colliding high-energy photons with intense lasers to create entangled electron-positron pairs. But that's more for fundamental physics research right now.
So big picture on creation. Photon entanglement often uses these, well, somewhat chancy optical processes. Electron entanglement, especially in quantum dots, leverages strong, controllable interactions, aiming for deterministic creation, which seems really crucial for building scalable quantum computers.
That's a key distinction, yes. Control versus probability.
All right, we've made them. Now, how do we prove they're actually entangled? Measuring seems like it would also be very different. Photons first, that sounds easier.
Relatively speaking, yes.
Yeah.
Photon detection is quite mature. Typically, you send each photon from your entangled pair to a separate measurement station.
Okay.
Each station has something like a polarizing beam splitter, which directs photons based on their polarization and very sensitive single-photon detectors.
And then you just count.
You measure the correlations. You see how often, say, you detect horizontal polarization at station A and vertical at station B. Then, crucially, you rotate your measurement settings, change the angles of your polarizers, and measure again.
Why rotate the settings?
To perform a Bell test. The correlations you observe across different measurement angles must violate a Bell inequality, like the CHSH inequality. If they do, it's statistical proof that the correlations are stronger than anything classical physics could allow. That's how you confirm non-local entanglement.
So measure correlations in different ways and check if they're too strong to be classical.
Exactly. You can also use interferometers to measure entanglement and other properties like momentum or time bends.
Okay, photons seem manageable. Electrons, though. Measuring the spin of one tiny electron trapped in a solid. That sounds incredibly hard.
It is much harder. An electron's magnetic moment, its spin signal, is absolutely tiny. Direct detection is basically impossible for a single electron spin in these systems.
Oh, how?
We use a really clever indirect method called spin-to-charge conversion.
Spin to charge, what does that mean?
It means we make the electron's location, whether it's in one place or another, which we can detect via its charge, dependent on its spin state.
How on earth do you do that?
A common way is to use a quantum dot positioned right next to an electron reservoir, like a sea of electrons. You carefully tune the energy levels using gates.
Okay.
Because of the Pauli exclusion principle and energy considerations, you set it up so that an electron can only tunnel out of the quantum dot and into the reservoir if, say, it's spin down. If it's spin up, the energy levels don't line up, or the state in the reservoir is already occupied by another spin-up electron, so it's blocked. It can't leave.
Wow, so tunneling spin down, no tunneling spin up.
Essentially, yes. Then you use an extremely sensitive electrometer nearby to detect the tiny electrical signal if that single electron tunnels out. A blip of current means it was spin down. No blip means it was spin up.
That is ingenious, turning an invisible spin into a detectable charge movement?
It's a remarkable technique. And they've gotten incredibly good at it, achieving single-shot readout fidelity, getting the right answer in one try of over 99%, often within microseconds.
Incredible. So even though the physical setups are worlds apart polarizers for photons, these complex spin-to-charge schemes for electrons, the ultimate proof is the same.
The ultimate logical proof, yes, Bell tests. The data, however you get it, has to show those non-classical correlations that violate a Bell inequality.
Or use entanglement witnesses.
Right. Entanglement witnesses are another tool. There's specific measurements designed so the result is, say, negative only if entanglement is present. It can sometimes be a quicker check than a full Bell test.
So the takeaway on measurement. Photon detection is mature, fast, direct, great for communication links. Electron spin measurement is complex, indirect, maybe slower, but it's the essential readout mechanism for these stationary quantum processors.
Exactly right. Different tools for different jobs.
Okay, we can create them, we can measure them, but keeping them entangled, that seems like the big hurdle. Let's talk about decoherence, the arch nemesis. What is it, fundamentally?
The decoherence is basically the process where a fragile quantum state, like superposition or entanglement, loses its quantum character because it interacts with its surrounding environment. The quantum information sort of leaks out.
It becomes more classical.
In essence, yes. The delicate correlations are washed away by noise.
How does this hit photons, the flying qubits? They seem pretty isolated out in space or fiber.
For photons, the main enemy isn't so much interaction noise, although that can happen scattering off air molecules, turbulence, things like that. The overwhelming problem is just photon loss.
They just disappear.
Yeah, they get absorbed or scattered out of the path as they travel through optical fibers or the atmosphere. Remember, entanglement involves at least two particles. If one photon from an entangled pair gets lost, poof, the entanglement is gone.
So distance is the killer for photon entanglement, primarily due to loss.
That's the main bottleneck for long-distance quantum communication, absolutely.
Electrons, then. Stuck inside a noisy solid-state device. Sounds like they have a tougher time with interaction noise.
Oh, much tougher. An electron spin qubit is never truly alone in there. It's swimming in a complex, messy environment. A major culprit is the hyperfine interaction.
Hyperfine.
The electron spin interacts magnetically with the spins of all the atomic nuclei in the surrounding crystal lattice, like tiny magnets all around it, constantly jiggling.
A spin bath.
Exactly. This creates fluctuating magnetic fields right at the electron's location, and that messes up the electron's spin state, particularly its phase coherence. We call this T2 time.
And its charge causes problems too, right? You mentioned charge noise.
Yes, definitely. Tiny fluctuating electric fields from defects or impurities in the material can physically jostle the electron because it's charged.
Like electrical static?
Kind of. And if you're using a magnetic field gradient to control the qubit, which is common, this physical jostling translates charge noise directly into magnetic noise for the spin. We call that transduced noise, and it can cause very rapid dephasing.
So its own charge betrays it. Any other major noise sources for electrons?
Yes. Spin-orbit coupling is another big one. This links the electron's spin to its motion through the lattice. So vibrations in the crystal phonons, which are like quantum packets of heat or sound, can interact with the electron's motion, and through spin-orbit coupling, disrupt its spin state. This can cause spin flips, limiting T1 time, or dephasing, limiting T2 time.
So it seems the very thing that makes electrons useful, being embedded in a controllable solid, is also their biggest enemy, environment-wise.
That's the trade-off, absolutely.
How do coherence times compare, roughly? And how do we fight back?
Coherence times for electrons vary wildly. In early materials like gallium arsenide, maybe tens of nanoseconds. But in highly purified silicon-28, where you remove almost all the nuclear spins.
It's a spin bath problem.
Right. In isotopically pure silicon, they've achieved coherence times of milliseconds, even seconds, for certain types of spin qubits. It's a huge material science challenge.
And for photons?
For photons, it's not really about time, but distance. Entanglement can be maintained potentially over hundreds of kilometers in fiber, but loss becomes prohibitive. We need quantum repeaters for longer distances.
So mitigation strategies. For electrons, it's cleaner materials, like that silicon-28.
Yes, materials engineering is huge. Also, using clever pulse sequences like Hahn echoes or more complex dynamical decoupling sequences, these act like refocusing pulses that can cancel out the effects of slowly varying noise, and operating the qubits at specific sweet spots in the control parameters where they're naturally less sensitive to certain types of noise.
And for photons? besides better fibers?
Quantum repeaters are the big hope for long distances. These are nodes that use entanglement swapping entangling segments piece by piece to overcome the exponential loss. Also, using more robust encoding, maybe using multiple photons or higher dimensional entangled states.
Okay, so the decoherence picture really reinforces the idea. Electrons are powerful, but fragile in their solid homes, needing protection. Photons are great travelers, but prone to getting lost on the journey.
A good summary. Which leads us directly into applications where these strengths and weaknesses define their roles. Stationary versus flying qubits.
Let's talk photon entanglement first. Quantum communication seems like its natural home.
Absolutely. The most mature application by far is quantum key distribution, QKD.
Secure keys.
Exactly. Alice and Bob use entangled photon pairs to generate a shared, secret random key for encryption. The security comes from the laws of quantum mechanics itself. If an eavesdropper, Eve, tries to measure the photons to learn the key, her measurement inevitably disturbs the entanglement in a way that Alice and Bob can detect when they compare a subset of their results later. It guarantees tamper detection. Entanglement-based QKD is particularly robust against certain attacks.
Very clever. And the bigger vision, the quantum internet.
That's the grand goal. A network that connects quantum computers and sensors, distributing entanglement between distant nodes.
What does that enable?
Oh, things like distributed quantum computing, linking smaller processors to tackle huge problems. Ultra-precise clock synchronization for navigation or fundamental science. And of course, secure communication far beyond what classical networks can offer. Photons are the obvious carriers for this, the quantum fiber optics.
People talk about linear optical quantum computing too, using just photons.
Yes, LOQC. It's theoretically possible to build a universal quantum computer using only photons, linear optical elements like beam splitters and photon detectors. But practically, it's very challenging because the required quantum gates are inherently probabilistic, meaning they don't always work, which leads to enormous overhead in resources and error correction to achieve scalability.
Okay, so photons dominate communication. Electrons then must be the heart of solid-state quantum computing.
That's where they shine. Electron spins, trapped in semiconductor quantum dots or bound to donor atoms like phosphorus and silicon, are really excellent stationary qubits.
Why excellent?
Well, scalability potential is huge. We can leverage the incredibly advanced semiconductor fabrication industry that makes our classical chips. They're tiny, maybe 100 nanometers across. And as we discussed, we can control their interactions strongly and locally using electrical gates, allowing for fast, high-fidelity two-qubit logic gates, the building blocks of quantum algorithms.
And entanglement is the fuel for these algorithms.
It's the essential resource. Quantum algorithms, like Shor's algorithm for factoring large numbers, or Grover's for searching databases, get their incredible speed up precisely because they can create and manipulate these massive, multi-qubit entangled states. This allows for quantum parallelism, exploring many possibilities simultaneously.
And you need entanglement for error correction too, right? Qubits are so fragile.
Critically important.
Yeah.
Real quantum computers will need quantum error correction, QEC, to be fault tolerant. QEC works by encoding the information of one logical qubit across many physical qubits, using specific entanglement patterns.
How does that help?
If an error occurs on one physical qubit, you can detect and correct it by measuring correlations between the physical qubits without actually measuring and destroying the fragile logical quantum information itself. Entanglement is the glue holding these codes together.
So entanglement is needed both to run the algorithms and to protect the computation. What about quantum sensing? Do both play a role there?
Yes, both can be used. Electron spins are fantastic sensors. Because they're so sensitive to their local magnetic environment, a single electron spin, like in a nitrogen vacancy, NV center in diamond, can act as an incredibly precise nanoscale magnetometer. People are using them to map magnetic fields with atomic resolution.
And photons for sensing.
Entangled photons offer advantages too. Quantum-enhanced microscopy, for example. You can use entangled photon pairs to probe delicate biological samples with much lower light intensity, reducing damage. Or you can use entanglement to achieve imaging resolution that surpasses the classical diffraction limit, seeing finer details than normal light allows.
That relates to the Heisenberg limit versus the standard quantum limit.
Exactly.
Yep.
With n-unentangled particles, measurement precision typically improves as the square root of n. That's the standard quantum limit. But with n-entangled particles, you can, in principle, achieve precision that scales directly with n, the Heisenberg limit, a potentially huge advantage.
So it really hammers home the point. This isn't electrons versus photons. It's clearly electrons and photons. Their properties make them natural partners.
Perfectly complementary.
Eh.
Electrons for the heavy lifting of processing as stationary qubits, photons for the long-haul communication as flying qubits.
Like classical computing nodes connected by fiber optics, but quantum.
That's a great analogy. Which brings us to the really exciting frontier. Synthesis and the future outlook. Hybrid systems.
Combining them.
Exactly. First, let's just recap the core similarities and differences we've hammered out.
Okay. Similarities. Both represent this universal, non-local quantum correlation. Both described by wave functions you can't factorize. Both verified by breaking Bell's inequalities. The weirdness is the same.
Right. But the differences are profound. Nature and constraints. Electron is a fermion, uses Pauli as a resource, allows deterministic generation. Photon is a boson. Probabilistic generation is common.
Environment and decoherence. Electron is stationary but stuck in a noisy, solid-state world. Photon is a flying qubit, relatively clean flight but prone to getting lost.
Manipulation and measurement. Electron has strong interactions, great for gate control, but measurement is hard and indirect. Photon has weak interactions, making gates difficult, but detection is relatively easy and direct.
Which leads straight back to those complementary roles we just discussed, processors and communicators.
Precisely. And the dream, the ultimate vision, is to build a seamless bridge between them. A robust interface.
A quantum transducer.
That's the term. A device that can faithfully convert quantum information back and forth between, say, an electron's spin state and a photon's polarization state, without losing the quantum coherence.
How would that even work? What's the concept?
Typically, the idea involves coupling a stationary spin qubit, like our electron, and a quantum dot, or maybe an NV center spin very strongly to an optical cavity, basically a tiny chamber made of mirrors that traps light.
Okay, spin plus cavity.
Then, you might use a laser pulse to excite the system. As the system relaxes and decays back down, it emits a single photon. But because of the strong coupling, the properties that emitted photon, its polarization, its frequency, maybe its timing, become entangled with the final spin state of the electron left behind.
So the photon carries away a quantum fingerprint of the electron's state?
Exactly. Or you can run it in reverse. Send in a photon with specific quantum properties, have it absorbed, and transfer its state onto the electron spin.
What does this let you do? What are the key functionalities?
Oh, huge things. Remote entanglement generation is a big one. Imagine you have two nodes, each with an electron spin coupled to a cavity. Each node emits a photon entangled with its local electron.
Right.
You send those two photons to a central station and interfere them on a beam splitter. If you then detect the photons in a particular way, that measurement projectively swaps the entanglement onto the two distant electron spins, even though they've never interacted directly.
Creating an entangled link between processors just using light?
Exactly. That's the basis for quantum repeater networks and connecting quantum computers. It also enables hybrid quantum computation.
Mixing different qubit types.
Yes, playing to everyone's strengths.
Oh.
Maybe you use super-fast, superconducting qubits for the main processing, link them via microwave resonators to slightly slower but longer-lived electron or nuclear spin qubits for memory storage, and then use photons coupled via transducers as the quantum bus to connect different modules or chips.
Wow. That sounds like the future. Are people actually doing this?
Progress is being made. It's incredibly challenging. But there have been breakthroughs. You mentioned that 2022 result, the first demonstration of entanglement between a free electron, like an electron microscope beam, and a photon using an on-chip optical microresonator. That was a landmark step towards interfacing different kinds of quantum systems.
Incredible. So what a journey we've taken. From Einstein's spooky action right down to the nitty-gritty of making electrons talk to photons via these transducers.
Yeah, we've seen how the universal weirdness of entanglement manifests very differently in these two fundamental particles, and how those differences, remarkably, make them perfect partners.
It really shows that what might seem like a limitation, like the electron's charge or the photon's weak interaction, is actually precisely what makes it suited for its specific role in this emerging quantum technology ecosystem.
Couldn't have said it better myself.
So, thinking ahead, what new frontiers really open up when we can truly seamlessly connect the brains, these electron-based processors, with the highways, the photon communication channels? What does that unlock?
Well, beyond the obvious, like scalable, distributed quantum computing, you start to wonder about more fundamental questions. Can we use these networks to perform new kinds of quantum experiments over vast distances? Could manipulating entanglement between matter and light across networks reveal deeper insights into quantum gravity or the nature of spacetime itself? It really reshapes how we think about distributing and processing quantum information.
It's a fundamental shift in handling information itself. So, the final thought for you, our listener: keep a close eye on developments in these hybrid quantum systems. They really are where the processing power of electrons meets the communication power of photons, and that convergence is likely shaping the next generation of truly world changing quantum breakthroughs.